Welcome all. This is Bharat and I'd like to talk to you about our work on combining implicit function learning and parametric models for 3D human reconstruction. Given a dense, sparse, or partial point cloud, we aim to produce detailed and controllable 3D reconstruction. We present implicit part network or IPNet that predicts from an unordered point cloud the outer dressed surface, the inner body shape under clothing, and simple part correspondences. We note that simple can be easily registered to the estimate smooth body shape using the part correspondences. We then non-rigidly deform this mesh with simple plus offsets model to fit the outer reconstruction in order to capture details corresponding to clothing, hair, etc. Next, we show our experiments with IPNet. Single view point clouds are easily accessible from devices such as Kinect. We show that IPNet can be trained to fully reconstruct the missing shape and also register simple to it. IPNet can estimate body shape under clothing. We evaluate our performance on the buff dataset. IPNet reconstructions are not just static meshes, but can be controlled using registered simple model. Given an input point cloud, we can obtain the simple registration using IPNet predictions. We can now animate this registration with a motion sequence. We demonstrate shape control using IPNet predictions. We add 20 kg weight and 20 cm height to the original animated registration. Our approach of combining implicit function-based reconstruction and parametric models generalizes well to other domains such as 3D hands. Thank you for your time.
We present Sizer, a dataset and model for parsing 3D clothing and learning size-sensitive 3D clothing. There is no existing work for size-sensitive clothing model, and subtle changes in the garment with size make the task very challenging. Moreover, there is no existing dataset capturing garment size variation in the real world. We introduced the Sizer dataset, which is a clothing size variation dataset. It contains approximately 2000 scans, which include 100 different subjects, 10 garment classes, and 4 garment sizes. The dataset includes clothing segmentations, SMPL plus G registration, and garment labels. Our proposed method is a tandem of two modules, namely ParserNet and SizerNet. ParserNet converts the SMPL registered meshes of a scan to multi-layered meshes of clothing and detailed body shape under clothing, without the need of scan segmentation during inference, which is a challenging problem in itself. SizerNet is a size-sensitive clothing model which predicts the deformation in garments conditioned on body shape and garment size. With this whole module, one can edit the garment meshes directly from a single mesh representation. We now present the results of our method. The key idea behind ParserNet is that it predicts the garment vertices directly as a convex combination of SMPL registered input mesh vertices. Hence, we preserve the details in input mesh, and predicted garment meshes are coherent with a common garment template for a garment class. We show the results of ParserNet for various garment classes. Now we show the result of the whole method, where we extract the garment from a single input mesh and resize the garment. We can also use SizerNet to drape the garment on new body shapes. We will release the dataset, code, and model for research purposes. Thank you.
We present NASA, an architecture to represent deformable articulated bodies with neural networks. The model receives as input a collection of coordinate frames and outputs a post-conditional occupancy function. In contrast, traditional 3D articulating models are manually authored by 3D artists by specifying control skeletons, polygonal meshes, and scaling weights. Non-trivial post-processing is needed to compute occupancies. We investigate 3 different architectural variants. The unstructured model represents the subject via a single neural implicit function. The rigid model decomposes the geometry as a collection of rigid parts. The deformable model allows parts to change shape according to poses. NASA improves the reconstruction quality by over 50% absolute. NASA can be used to implement robust dense tracking in just a few lines of TensorFlow code. In comparison, traditional dense tracking pipelines are complex and require careful engineering. Come to our session to find out more.
I want to introduce our work Unsupervised shape and post disentanglement for 2D meshes. Given an input mesh, our objective is to encode it into latent space that is composed of disentangled shape and post components. Our method is based on two key ideas. First, shape code should not change within a motion sequence, which we enforce with cross-consistency constraint. Second, changing post should not affect shape, which we enforce with self-consistency constraint. Here, we transfer motion from shape source on the left to post sources on the right. We can also interpolate shape code to obtain intermediate frames. We can interpolate post code as well. Thank you for your time.
Welcome to our paper, Kinematic 3D Object Detection in Monocular Video. We observed that temporal cues are not used in monocular 3D object detectors, which often causes orientation and localization to suffer through time. Therefore, we propose a kinematic model which can leverage video with two important benefits. First, it naturally is able to extract important scene dynamics, such as ego motion and per object velocity. Second, it helps improve the stability overall of the estimated 3D boxes. We use a single network to estimate 3D boxes, ego motion, and use an integrated 3D Kalman filter for aggregation through time. We also introduced two key novelties which are synergistic to the Kalman, a self-balancing uncertainty and a more stable orientation. Our kinematic method improves accuracy, dramatically reduces orientation error, and provides reasonable estimations of ego motion and per object velocity. Thank you, and for obviously much more details on our method, please come to our session and discuss.